Students, the screen is visible, right? Is it visible?
Yes, sir, visible.
Yeah. Uh, Students, am I audible? Hello. Am I
Yes, sir.
audible? So in the last class, I have given some introduction about natural convection and forced convection. Am I correct? Am
Yes,
I
sir.
correct, students? Yeah. Can anyone of you say a few differences between natural and forced? What is the difference between natural and forced convection? 43 students were there. Vishwapriyan, Akash, Akhilesh, Anish, Anirudh. Anyone?
In natural
Next week,
convection,
next week we are supposed to be there inside the classroom, right? We will be meeting inside the classroom. Okay, fine. Go ahead. Yes, in case of natural convection.
in case of natural convection, the fluid flow is caused because of density variation, which in turn causes the heat transfer.
Okay, very good.
And in forced convection, it's caused by external means with a pump
Yeah,
or
very good. Okay, okay, very good. Fine, fine, fine. So we have discussed about the differences, and similarly, in case of uh, uh, forced convection as well as natural convection, we will be having that is a flow over a surface and a flow inside. Especially in case of forced convection, we have flow inside a surface. I have told you the examples of the hot that is hot coolant which flows inside the pipes in case of nuclear reactors. Similarly, water gets converted into steam. Okay, and then condensing of steam also we have discussed. Okay, so flow, internal flow and external flow. External flow is flow over a surface, internal flow is flow inside a surface. Okay, and similarly convection, right? Convection is more effective in transferring heat when compared to conduction. Okay, and again it depends upon the convective heat transfer coefficient. See, we know that yeah, we know that Q equal to HA del T, right?
yes, sir.
Which we have yeah, this the equation is there already. So heat flux which is equal to H into Ts minus T infinity, where H is nothing but the convective heat transfer coefficient, Ts is nothing but surface temperature, and T infinity is nothing but the surrounding fluid temperature. Okay, and H is said to be the local heat transfer coefficient, and it varies along the surface. Okay, so that's why often we will be considering the average friction coefficient. Okay, not the local friction coefficient. Okay, so whenever you are asked to find the heat transferred, okay, you should use h bar as into ts minus t infinity, that is equal to q, average heat transfer coefficient. Okay, average heat transfer coefficient you have to find out. Local heat transfer coefficient, it is specifically for a particular point. Okay, so this expression we have got it, this expression from the Newton's law of cooling. Okay, Newton's law of cooling says the heat transfer is directly proportional to the surface area and the temperature difference between the two, and we have got this heat transfer coefficient, convective heat transfer coefficient H, uh, which is which varies for different fluids. Okay, or in other words, Q equal to yes. Somebody, anyone wants to ask question? Okay. Uh, So, Q equal to HA del T, on where H is nothing but the convective heat transfer coefficient, and as I mentioned earlier, right, for liquids it is greater, and for gases it is lesser, which we have discussed earlier. And convection is usually conduction plus advection. Okay, conduction plus advection, and usually convection involves bulk motion of the fluid over a surface. Okay, bulk motion of a fluid over a surface, or the heat transferred from a surface to the fluid, or from a fluid to the surface, vice versa. Okay, I already told you about the examples, right? Hot coolant, liquid sodium flows inside the reactor core. It takes the heat energy and it gives the heat energy to the surface, and over the surface you will be having the water which flows inside. All of you are able to understand that? I have shown you on that day. Am I correct, students? All of you remember that?
Yes, sir.
The nuclear reactor which I have shown,
Yes,
I
sir.
think it's there in engineering thermodynamics. In very first introduction to engineering thermodynamics, we used to say that production. Whenever I handle engineering thermodynamics, I will be showing this. Okay. Uh, So you can see here, this is the hot coolant, right? The red color one is nothing but the hot coolant, which is nothing but the liquid sodium. Now what happens is, I have already told you, convection is conduction plus advection. Okay. So now what happens here is, the from the hot reactor core, okay, the coolant takes the heat energy, liquid sodium, and it passes through the tube, and it transfers the heat energy to the tube material. Okay, so that's why the tube material should have higher thermal conductivity, so that it can transfer the heat to the circulating water, so that the water gets converted into steam. And the steam runs the turbine. We know that we get the energy. Okay, so it depends upon, but our concept is the heat transfer by means of convection. Okay, so we say heat transfer by means of convection is much more higher when compared to heat transfer by means of conduction. Okay, so that's why what happens here is, the heat possessed by the coolant will be higher when compared to the heat transferred to the water, right? So now here you can see here, from the hot coolant to the um, tube surface, and from the tube surface to the surrounding water. Okay, hot coolant may be liquid sodium, and the water is the one which will be at a higher pressure. It gets converted into steam in the steam generator. Okay, so this particular thing you should know. Okay, whenever we talk about uh, uh, the heat transfer in case of nuclear reactors. Okay, so especially in case of power plants and nuclear reactors, um, the heat transfer, right? The heat transfer is very much important, and even yeah, I don't want to go further into it. Okay, let's stop with that. Okay, now when we talk about this, okay, let me have this. Let me draw this. Is it visible here?
Yes, sir.
Yes, sir.
Yeah. So whenever we have a flow over a flat plate, assume this is a flat plate. Okay. Now assume the velocity of air which passes at u infinity. Okay. Now what we have is, when the fluid particles touch this surface, this edge is said to be the leading edge. Okay, the edge which is leading edge. Leading edge is the one which faces the flow, and trailing edge is the one which is at the rear end. Okay. Why this concept is very, very important, especially flow over flat plate cylinders and spheres were very, very important, because especially when we talk about aeroplanes, we have the aeroplane wings. Am I correct, students? You will be
Yes, sir.
having the airplane wings, and the air will be passing over the airplane wings. Okay, so now this is very, very important. Okay, now what happens is, the fluid particles, right? The fluid which flows at a velocity u infinity, it is stopped here, right? It is stopped here, so that what happens is, there will be small flow of this, the escaping of this fluid particles. Okay, since it is stopped, okay, it will try to, the fluid particles will be try to move over. Okay, so that what happens is, generally we will be seeing a small boundary layer, okay, which gets formed from this leading edge up to the trailing edge. Okay, and the maximum thickness of the boundary layer we will be seeing at the trailing edge, and usually it is given by del. Okay, and the boundary, which one defines the difference between the boundary and this one? See, now what happens here is, inside this boundary layer, the the value of the velocity of the fluid flow particles will be varying from 0.1 times of u infinity to 0.99 times of u infinity. Okay, so at the boundary it will be 0.99 times of u infinity. So above which the velocity of the fluid particles will be equivalent to u infinity. Okay, so within the boundary, what happens? It varies from 0.1 times of u infinity to 0.99 times of u infinity. So that imaginary layer is said to be the boundary layer, and this is said to be velocity boundary layer. Okay, so which purely depends upon the velocity of the fluid. All of you are able to understand this, students?
Yes, yes, sir.
Students, okay. What I try to say is, I have a plate. Okay, I have a plate. Fluid particles were passing over it. Okay, and see, at a certain distance, the fluid will be flowing at u infinity only. Okay, but what happens is, so since the fluid particles were stopped, right? When the fluid particles were stopped, here the velocity of the fluid particle is zero. Okay, but above it, you will be having a small boundary layer thickness where the velocity of the fluid particles will be in between 0.1 times of u infinity to up to maximum 0.99 times of u infinity. Okay, so from 0.1 to 0.99, that particular area is said to be the boundary layer area, and beyond which you will be having the uh, original velocity u infinity. Okay, so this is a small layer, and this boundary layer thickness is usually mentioned as del. Okay, usually it is mentioned as del. Okay, now what happens here is, uh, this boundary layer thickness depends upon so many uh, properties. Okay, it depends upon velocity, it depends upon the mu, which is nothing but the viscosity, and it also depends upon the k value. Okay, thermal conductivity value, and it also depends upon the cp value, specific capacity. It depends upon so many things. Okay, viscosity, thermal conductivity, specific capacity of the fluid. Okay, students, all of you are able to understand this velocity
Yes, sir.
boundary
Yes,
layer.
sir.
Okay, this is what mentioned here. Okay, in the slide when you see this, okay, the fluid flows over at a velocity u infinity and at a temperature t infinity. Okay, and it flows over a flat plate. This is x-axis and this is y-axis, and at y equal to 0, at this point the velocity u infinity is equal to 0, because the fluid particles were brought to rest at this point. Okay, this is what I was mentioning. The fluid particles were brought to rest at this point. Okay, the fluid particles were brought to rest at this point. Okay, and so that's why what happens is, usually in case of airplane wing design also, okay, the edge will not be a uh, will not be having this perpendicular thing. Okay, it will be in the form of I don't know how many of you have noticed, it will be in the form of v. Even the aeroplane shape is also in the form of v, so that what happens is, the wings. Okay, so that what happens is, the fluid will be easily flowing over, above and below the aerofoil shape. Okay, even the cars, okay, whatever cars we have, it will be having this shape. Okay, and what happens is, so that the fluid will be passing over it, and it will be passing over. Okay, so that's why in the olden days even the cars were of this shape. Okay, so that easy flow of the air and wind resistance will be lesser. And you know this, especially when you travel in Wagoner, okay, which is more or less rectangular in shape, and when you have a car, okay, travel by other cars where you will be having this shape, the wind resistance is lesser for this type of vehicles when compared to rectangular shaped vehicles. Am I correct or not? Am I correct?
Yes, sir.
Even when you travel through a small Maruti car, and when you travel with a wagoner in highways, you experience this. Okay, so whenever the body shape is rectangular, the wind resistance acting on it is more when compared to the aerofoil shape. Okay, so that's why the aeroplanes, you will be having this aerofoil shape. Okay, okay, students. So that easily the fluid particles will be moving up, above and below easily. Okay, so that's one of the important concepts you have to understand. Okay, and now when we talk about the heat flux, okay, we know that Q double dash, which is equal to H del T, or Q equal to H A del T. Okay, now this H bar is nothing but the local heat transfer coefficient. Sorry, average heat transfer coefficient. Okay, H is nothing but local heat transfer coefficient, and H bar is nothing but average heat transfer coefficient. Why we have to consider the average heat transfer coefficient? Because the local heat transfer coefficient is pertain to a particular point or at a particular distance of x from the over the total length. Imagine that you have a flat plate here. Okay, so up to a particular point x from the leading edge. Okay, so this is the overall length. Okay, so overall length L. So the local heat transfer coefficient is the one which is specific about a particular point, whereas the average heat transfer coefficient from 0 to x, okay, is taken as h bar. Okay, it is h bar, whereas local heat transfer h defines at a particular point, and this h value varies from 0 to x, and similarly 0 to l. Okay, so that's why usually the average value is considered. Why it is so? Because you may know that Reynolds number is equal to ux divided by nu. Okay, so the viscosity value, the velocity value, and the distance value. Okay, so the increase in distance and the viscosity value. So the Reynolds number will not be constant from at x equal to 0 to x equal to L. Okay, so generally in case of heat transfer calculations, we will be considering H bar, which is nothing but the average heat transfer coefficient. We will not be considering the local heat transfer coefficient, or in other words, H bar, which is equal to 1 by L over the entire length, integral 0 to L H dx. Okay, why it is so? Because the local value and usually by calculation purpose, when you look into the calculations, you may see that x equal to 0 to x equal to l, it varies, and the average value is usually considered. What happens is, if you put x equal to 0.1 for a length, assume the length is 1 meter, x equal to 0.1 to x equal to 1, you will be having variation in the h values, and the overall average value is usually taken. Okay, the overall average value is usually taken, and there are so many assumptions which you have to understand when we go for this finding out of this h value. What are all the assumptions which we consider? Okay, so the assumptions which we consider is, usually what happens is the boundary layer thickness increases as a distance uh, that is a distance from the trailing leading edge to the trailing edge. Okay, so the boundary layer thickness decreases when u infinity increases. When u infinity increases, if the velocity is so high, the boundary layer thickness reduces. Okay, having instead of having boundary layer thickness like this, okay, if the velocity is too high, then the boundary layer thickness will be less. Okay, if the velocity is moderate or average, then you will be having higher boundary layer thickness. Okay, so the the thickness which is measured perpendicular to the uh, x-axis is usually said to be the boundary layer thickness, which is given by del L. Okay, del is used to define the boundary layer thickness. Okay, if the velocity of the particles is so high, u infinity is very high, then this boundary layer thickness reduces, and layer thickness increases from x equal to 0 to x equal to L. Okay, whatever may be the velocity, you can see here, it is lesser here and it increases. Okay, at the end, it will be del also increases with increase in viscosity. Okay, so that's why viscosity is often considered. And we also know that usually the flow over the flat plate, it is decided whether the flow is laminar or turbulent. It is decided by the dimensionless number, Reynolds number, which is given by ux divided by nu or ul divided by nu. Okay, and if this value, the nu is nothing but the viscosity. Okay, often, yeah, let me show you. Students, these few points are very, very important. Please concentrate. See, often when we want to find out the properties, I ask a question. Now, usually air is assumed to be the fluid which flows over a surface. The properties of air will be in page number 33. Yeah, I think properties of dry air. Am I correct, students? Is it visible?
Yes, sir.
Yes, sir.
Okay, ma. Now, let me ask a question. Now, you have surface temperature of the flat plate as 100 degrees C, and T infinity is equal to 25 degrees C. Now, I ask you a question. At which temperature you will be calculating the properties? Whether you will be taking the properties at 25 degrees C or you will be taking the properties at 100 degrees C. Some of you have started that is natural convection, forced convection experiment in PinFin last week. Yes,
Yes.
Sir, we took around 40.
40. Why 40? 20 is the sorry, 25. 25 is the T infinity. 100 is
Oh, sir,
the
sorry, 30.
hmm? We should be
Okay.
taking the film temperature. All of students, please understand, we have a concept. We will be taking the values at film temperature, which is nothing but Ts plus T infinity divided by 2. So 100 plus 25, the property should be evaluated at a temperature 125 degree divided by 2, which is nothing but 62.5 degrees C. Okay, so we have to take the values at film temperature. We have the boundary layer thickness. Okay, and so just like U infinity, I had told you here it is 0.1 times of U infinity, and at the edge it will be 0.99 times of U infinity. Similarly, we have thermal boundary layer. Okay, so in case of thermal boundary layer, what happens is you will be again we have the leading edge. Okay, Ts T infinity. So 20 degrees C, Ts may be 100 degrees C. Okay, now what happens here is here you will be having zero point 0.1 times of T infinity, and at the end you will be having 0.99 times of T infinity. Or in other words, okay, the temperature reduces, right? The temperature reduces from the surface up to the boundary, and at the boundary the temperature will be more or less equal to the 99 percentage value of the 99 percentage value of the temperature of the air or the fluid. Okay, so this is said to be thermal boundary layer. Okay, just like velocity boundary layer, you have the thermal boundary layer concept also. And velocity boundary layer, and thermal boundary layer. Okay, both the things you have viscosity. Viscosity of the fluid is very much important. Thermal conductivity of the fluid is important. Specific capacity of the fluid is important. So that's why we will be taking the film temperature. We will not be taking the temperature of the air. Often students do the mistake. Okay, usually a flat plate is given in the problem, and fluid over flows over it at say 40 degrees C. Flat plate will be at 100 degrees C or 80 degrees C, like that. Okay, so you have to take the average temperature, which is nothing but the fill temperature TF. Okay, so you can see here, even in the data book, forced convection. There's a page number for forced convection. Forced convection 112. Now you can see here at the very first thing, film temperature. The properties are to be evaluated at film temperature unless otherwise it is stated in the question paper. Okay, it has to, you have to evaluate it as film temperature, and you can see here del Hx is nothing but 5 into x into Reynolds number per minus 0.5, and del Tx is del Hx into Prandtl number. PR is nothing but the Prandtl number. Okay, and Cfx is nothing but the local friction coefficient, and CFL bar is nothing but the average friction coefficient. So no need to find out the local friction coefficient. You have to find out the average friction coefficient. Okay, so you can use the different expressions to find out the Nusselt number, and finally Nusselt number. See, you will be having using Nusselt number and Grashof number in this. Okay, so the Grashof number is nothing but it is the product of buoyant force by viscous force into inertia force by viscous force, or in other words, buoyant force into inertia force divided by viscous force whole squared is nothing but Grashof number. And Nusselt number. Nusselt number is nothing but ratio of temperature gradient by conduction to the ratio of to the convection at the surface. Okay, so you may ask a question, sir, whether Bayer number and Nusselt number are same. No, because both the things were HL by K or HT by K. So if it is diameter, if it is a cylinder or sphere, we have to take the diameter. If it is a flat plate, then we will be taking the length. Okay, so Nusselt number is equal to HL by K. Similarly, here we have Bayer number is also equal to HL by K. But Bayer number gives us an idea about internal conduction resistance to surface convection resistance. It is a ratio. Whereas here, Nusselt number is nothing but ratio of temperature gradient. Okay, the temperature gradient by conduction to the temperature gradient by convection. Okay, so that's the difference between the Bayer number and Nusselt number, which you should know. And Reynolds number, we know that it is nothing but ratio of inertia force to viscous force. So UL by nu or UD by nu or UD rho divided by mu. Okay, so when we take the data book, we have to take the new value, which is nothing but the viscosity. Let me show it. So even flue gases, sometimes they will give you the question in the question paper. So if flue gases were given, argon is given, or some other is given, then sulfur dioxide or carbon dioxide, if it is given, then you should take the value. So new value is nothing but kinematic viscosity. Mu is nothing but the absolute viscosity. So you have to take the new value only. Kinematic viscosity you have to take. Alpha you have to take. Prandtl number you have to take. Okay. Why Prandtl number? Because the Prandtl is the scientist who has given this concept of finding out the local friction coefficient and average friction coefficient. Now you may ask a question, sir, what are all the assumptions which they have taken, or what are all the thicknesses which we have? Okay, so actually we have three thickness. One is displacement thickness, the second one is momentum thickness, and the third one is energy thickness. Okay, displacement thickness, momentum thickness, and energy thickness. Okay, displacement thickness is usually it is defined as the distance measured perpendicular to the boundary. See, the distance measured perpendicular to the boundary. Okay, at any point from x equal to 0 to x equal to L. Students, all of you are able to understand this? Students,
Yes,
displacement
sir.
thickness. So from x equal to 0 to x equal to L, if you measure the thickness perpendicular to the boundary, then it is usually said to be the displacement thickness. Okay, and the second one is the momentum thickness. In case of momentum thickness, it is the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for reduction in momentum. See, what happens is when fluid flows over, right? When fluid flows over, often we have the drag force, right? See, especially aircrafts, some other persons, some of you might have uh, went through, some of you or most of you have experienced flying in aeroplanes. Okay, so sometimes we used to have the term known as turbulence. Okay, so much turbulence was there. The reason being is when the aircraft propels at a faster rate, then the turbulence also increases. We know that. Okay, see, what happens is the drag force. Okay, so due to the high speed of the incoming velocity of air, what happens is a drag force is created, or the surface, okay, it moves the surface. Okay, it moves the, or it drags it, or it pulls it. Okay, so this force is very much higher. Okay, so when we consider that, okay, the displacement of the body, then we will be talking about momentum thickness. And similarly energy thickness. And again, when we talk about energy thickness, uh, usually it is the distance measured again perpendicular to the boundary of the solid body, and usually by which the boundary should be displaced to compensate for the reduction in kinetic energy of m u squared is the kinetic energy. We know that the kinetic energy of the fluid is half m u squared, where u is nothing but the velocity and m is nothing but the mass of air. Okay, and the mass of air usually we calculate it as mass by volume, which is equal to density, or m, which is equal to rho into u, density into um, volume. Okay, often we talk about the volume. Okay, we don't talk about the area, we talk about the volume. Okay, volume of the solid, volume of the aircraft. Okay, volume inside the aircraft. Okay, so often we, so density into area, density into volume. Okay, so from like that, we will be having three thicknesses. One is displacement thickness, the other one is momentum thickness, and the other one is energy thickness. So we will be considering displacement equation, momentum equation, and energy equation. Okay, after considering all these things, Prandtl arrived at these expressions. Okay, and he found that the local friction coefficient, CF, which is equal to wall shear divided by, and that is the shear force. Okay, wall shear divided by kinetic energy of the fluid. Okay, so the kinetic energy of the fluid, we know that off into rho into u infinity squared. Okay, so here density is considered. Okay, and wall shear. Okay, shear stress is also considered. Okay, and similarly the surface frictional drag is calculated by tau s into as. Okay, tau s is again cf into rho into u infinity squared by 2. So the wall shear tau s is cf into rho into, all of you are able to understand this? Cf, which is equal to wall shear by kinetic energy, or wall shear is equal to cf into rho into u infinity squared by 2. All of you are able to say this, students? Am I audible?
Yes, sir.
Am I audible? Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, so the drag force is calculated with this, and CF is calculated with this. Okay, and tau s at y equal to 0 is mu into dou u by dou y at y equal to 0. Okay, so you may ask what is y? So this is x axis and this is y axis. Okay, at y equal to 0, at this point at y equal to 0, tau s, which is equal to mu into dou u by dou y at y equal to 0, where mu is nothing but again the dynamic viscosity of the fluid. Okay, so that's why mu value is also given in the data book, and nu value is also given in the data book. Okay, so if you want to find out density is also given. Okay, rho is given, mu is given, nu is given. Okay, kg per meter cube, uh, Newton second per meter. N stands for Newton. Am I correct? Am I correct, students?
Yes, sir.
Yeah, Newton second per meter squared. Okay, and whereas nu is kinematic viscosity is given in meter squared per second. Okay, so now what happens here is you will be for calculation purpose we will be taking new Prandtl number, CP value, and K value. Okay, and all these things has to be evaluated at the film temperature, not the temperature of the solid or not the temperature of the fluid. Okay, when it comes to convection, okay, convective heat transfer, whether it is natural convection or forced convection, the first important thing what you have to do, you have to find out the film temperature and you have to take the properties. When you find the film temperature and when you take the properties, out of 10 marks, 2 marks will be awarded. Please understand that. See, step by step, and I don't know, some other students even in Cat 1 they didn't do it properly. See, that is very, very important. Okay. So when you find the film temperature and when you take the properties for the corresponding fluid. Okay. Suppose if it is given as carbon dioxide, you have to take the carbon dioxide. If it is given as air, nitrogen, you have to take nitrogen. If it is given as air, properties of air, then you have to take the properties of the dry air. Okay. So this is very, very important. And the fluid is also important. Okay. In case of internal flow also, I already told you internal flow problems, liquid sodium may be given. Okay, liquids, you can see here properties of gases is there. Steam, properties of sometimes steam will be given, steam at 200 degrees C. So again the steam properties you can see what is rho, what is mu, what is nu, alpha, specific heat capacity. The specific heat capacity of liquid is and steam is slightly higher. And similarly when we talk about other fluids, other liquids, liquid salt, liquid metals. Properties of liquid metals is also there. Ammonia, hydrogen, these were gases. Yeah, you can see here liquid sodium. Properties of liquid sodium, liquid alloy. Okay, sodium potassium solution. Okay, bismuth, plumbum. Plumbum means lead, I think. Am I correct? PB. PB stands for
Sir.
lead. Okay, sodium, liquid sodium. You can see the properties here, and similarly liquid potassium, lithium, bismuth. Okay, and mercury, tin. Okay, so the new value, alpha value, Prandtl number value, CP value, and K value, you can get it. Okay, so please understand, it's not often air will be given immediately. Students will be taking, okay, air at say 40 degrees C. If it is air, then immediately students will be taking at 40 degrees. But you should not take at 40 degrees, so you should take at the film temperature. Properties has to be evaluated at the film temperature. So surface temperature plus air temperature divided by 2. So T infinity is only 40, and surface temperature may be 100 degrees or 80 degrees or 90 degrees like that. So 90 plus 40 divided by 2. So this is very, very important. Ts plus T infinity by 2. Is it okay, students? You may think, oh, why sir is teaching this subject like a mathematics teacher. Finally, you have to solve the problems also. That's very, very important. Numericals in the examination. Okay, so that's why I'm saying again and again. Shall I move on to the next slide, students? Shall I
Yes,
move
sir.
on? Okay.
Okay.
And similarly, when we talk about the thermal boundary layer, also the thermal boundary layer thickness, again the temperature varies. You can see that the temperature distribution Ts minus T divided by Ts minus T infinity equal to 0.99. Okay, so the surface temperature minus the temperature of the temperature at any point is in between 0 to 0.99 times. Okay, at this point it is 0 times of T infinity. At this point at the end it will be at the boundary it will be 0.99 times of T infinity. Okay, so the boundary layer thickness is defined as the value of y at which Ts minus T divided by Ts minus T infinity equal to 0.99. So the maximum thickness will be at this end, the thermal boundary layer thickness, okay, which is equivalent to 0.99 times of the temperature difference between the solid and the fluid. Okay, or at this point the temperature will be almost what's that 99 percentage of T infinity. Okay, so that's what you have to understand when we talk about the thermal boundary layer thickness. And what is the difference? Okay, what is the difference between the Yeah, of course, when we talk about velocity boundary layer, we have boundary layers. We have velocity boundary layer, thermal boundary layer, and concentration boundary layer. So, concentration boundary layer is purely mass transfer. We did not bother about it. Okay, as far as heat transfer is concerned, we will be having velocity boundary layer thickness del, whereas thermal boundary layer thickness is given by del suffix t. Okay, so that's why even the data book you can see here, page number 113. Yeah, now you can see here del Tx, del Hx. Okay, hydrodynamic boundary layer thickness is nothing but the velocity boundary layer thickness, and del Tx is nothing but del Hx into Prandtl number power minus 0.33. Is it fine, students?
Yes, sir.
Yes, sir.
So, velocity boundary layer thickness, you have to find out del Hx. Okay, thermal boundary layer thickness, you have to find out del Tx. Is it fine?
Yes, sir.
Yes, sir.
Okay. Okay, and for different cases and laminar turbulent combined, we will look into it. I will show this. Okay. Now, when we talk about the fluid flow over the surface. Okay. So I have shown here the air is flowing at a certain velocity u infinity over the surface. Now, what happens is if the fluid velocity u infinity is so high. Okay, if it is so high, then what happens is fluid flow over the surface. The fluid flow over the surface, it will be at beginning it will be laminar, and then there will be some transition stage, and then it will become turbulent. Okay, so in case of turbulent flow, okay, the fluid particles will be flowing in a zigzag manner. In case of laminar flow, the fluid particles will be moving in a straight line manner or in a streamlined manner. Okay, and there will always be a transition stage at which the fluid becomes laminar to turbulent. Okay, so laminar flow region, you will be having if the velocity is too high. Okay, if u infinity is too high, then you will be having uh, inside the boundary layer, you will be having laminar flow region, transition region, and turbulent region. Okay, so how to get this? Okay, we will be getting this with the help of Reynolds number. Okay, for internal flow, inside cylinders or inside tubes, the critical Reynolds number is 2300, and for external flow over flat plate only, the critical Reynolds number is 5 into 10 power 5. Okay, so we know that it is nothing but Reynolds number is inertia force by viscous force. Am I correct, students? I have already told you
Yes, sir.
Reynolds number is inertia force by yeah, even in the slide I have this. Reynolds number is equal to inertia force by viscous force. For Prandtl number is momentum diffusivity by thermal diffusivity, and Nusselt number is HL by K or HD by K, and Stanton number, Skimmett number, Sherwood number. These are all some of the numbers, dimensionless numbers, which we will be using. Okay, and what is the significance for Prandtl number, and how it varies for liquid metal, gases, water, liquid organics, oils. Okay, so this particular thing is very very important. I will be discussing about this in the next class. That's why theory is very very important. Of course, we will solve problems. Okay, and the boundary layer thickness and thermal boundary layer thickness and velocity boundary layer thickness depends upon the Prandtl number del by del t, which is equal to Prandtl number per n, where n is a positive integer. Okay, and it varies for liquid metals and it varies for oils. Okay, so that is the difference. Okay, so we will discuss that. Okay, about that in the next class. Okay, because it's see, this diagram will gives us an idea about del t is lesser, or thermal boundary layer is lesser when compared to velocity boundary layer in case of oils, whereas in case of liquid metals, the thermal boundary layer is higher when compared to velocity boundary layer. So that's why liquid metals were used for in nuclear reactors. This is very very important, or in other words, the Prandtl number is very much lesser, and the kinematic viscosity is very much lesser when compared to thermal diffusivity. What is thermal diffusivity? In the very first class itself, I had told you about thermal diffusivity. Thermal diffusivity is the one which gives us an idea about how faster the fluid gets heated or cold, or the metal gets heated or cold. Okay, it gives the degree of hotness or coldness. Am I correct? Am I correct,
Yes, sir.
students?
Yes, sir.
So the alpha value is very much higher for liquid metals. That's why the liquid metals have got more thermal boundary layer thickness when compared to velocity boundary layer thickness, and that's why liquid metals. At the beginning of the class, I told you liquid sodium is used, liquid potassium is used. Am I correct, students? In nuclear reactors, am I
Yes,
correct
sir.
or
Yes.
not here?
Yes, sir.
So
Yes, sir.
larger the thermal boundary layer thickness, more the heat transferred, more the heat transferred to the surrounding fluid. Okay, so that's very very important. More the heat transfer to the solid. Okay, here in case of liquid metals, the liquid metals will be at a very high temperature when compared to the plate. Okay, so more heat is transferred to the plate, and from the plate or tube, from the tube to the water. Water will be flowing outside, and liquid metal will be flowing inside. So that more heat transfer. And when we take oils, okay, when we take oils, the velocity boundary layer is higher, and thermal boundary layer is very less. Okay, and for liquids sorry, and for air and gases, for gases, the thermal boundary layer and velocity boundary layer will remain the same. Prandtl number equal to 1. See, in case of oils, Prandtl number is very much greater than 1, and in case of liquid metals, the Prandtl number is very much lesser than 1. Okay, so this particular concept, this is very very important when we want to do research in heat transfer, right? When we want to do research in heat transfer, right? And that's why even in IC engines, we talk about convective heat currents, convective heat transfer coefficient. For air and gases, Prandtl number is equal to 1. Okay, and for liquid metals, it will be higher, and for oils, it will be lesser. The thermal boundary layer is lesser. Okay, so this is very very important. You may think you may use different fuels. Okay, you may use you may use petrol, diesel, etc. But the new value and alpha value is also very, very important, especially in deciding the efficiency in a micro level. When we do research in micro level, okay, often UG students you will be calculating the brake thermal efficiency, etc. But when we want to use different fuels and when we want to study the impact of that particular fuel in the efficiency, we have to consider all these things. Okay, so that's why hydrodynamic boundary layer or velocity boundary layer and thermal boundary layer. Um, are very very important. Okay, and similarly I have spoken about the Reynolds number. Reynolds number gives us an idea about the whether the flow is laminar or turbulent, and up to what distance it is laminar and then it is turbulent. You can see here, flow or a flat plate, velocity is u infinity. uh, Up to a certain distance you will be having laminar flow, and then transition takes place, and then afterwards it is turbulent. Okay, and what is the critical Reynolds number for inside flow or internal flow? Critical Reynolds number is 2300. For flow or flat plate, it is 5 into 10 power 5. Okay, it is flat plate alone. When we talk about flow cylinders and sphere, it is it will be different. Okay, and we know that laminar flow is nothing but ordered fluid motion with identifiable streamlines on which fluid particles move. Turbulent flow. In case of turbulent flow, irregular fluid motion will be there. Okay, so tomorrow also we will discuss about this, and finally, uh, this particular slide is also very very important. Okay, how to get the local friction coefficient, how to get the average friction coefficient, and how to find the heat transferred by means of convection. Okay, so tomorrow we will be discussing again all these things. Okay, the effect of Prandtl number, and finally, uh, yeah, I will upload this today itself, and I'll be solving this particular problem. First problem number 1 tomorrow. Okay. Okay, students, is it fine? Let me stop the recording with this. If you have any questions also, you can ask. One of the student, he okay, that's not an issue. Let me stop the recording.